All right, let's get right into it. Welcome to today's explainer. We're tackling something absolutely crucial today, bridging that notoriously wide gap between Python, the easy-to-read language we all know and love, and the raw, massively parallel processing power of a GPU. You know that feeling when you're just sitting there, staring at a progress bar, crawling across your screen for hours while your machine crunches numbers? Yeah, CPU limits can become a major bottleneck. But today, we're looking at a tool designed to completely shatter that bottleneck, letting you execute code in a massively parallel way. Now, I know this might sound almost too good to be true, but what if you could tap into the massive parallel power of an NVIDIA GPU without having to learn or write a single line of C++? Seriously, not one line. That is the ultimate promise we're digging into today. We're going to see exactly how to achieve blazing fast performance using the exact same Python syntax you likely already know, specifically zeroing in on element-wise operations on NumPy arrays. To really appreciate how much of a game changer this is, let's look at how things are usually done. Traditionally, if you want to program in CUDA, which is NVIDIA's compute platform, you're looking at using CUDA C or C++. And hey, it's highly performant for sure, but it also means climbing a heavily steep learning curve and making massive modifications to your existing Python applications. Well, enter Numba. Instead of forcing you up that grueling C++ mountain, Numba basically just straps a rocket directly to your Python code. It takes a Python-first approach, giving you massive acceleration while letting you write code directly in Python, usually with barely any modifications at all. So what actually is Numba? By definition, Numba is a just-in-time type-specializing function compiler for accelerating numerically focused Python for either a CPU or GPU. Okay, I know that is a total mouthful. Let's break it down. First off, it's a function compiler, meaning it compiles specific functions, not your entire application. Second, it's just in time. It translates those functions at the exact moment they're first called, which makes sure the compiler knows exactly what argument types you're using. And finally, it's numerically focused. It works best with numerical data types like integers and floats, making it an absolute perfect match for NumPy arrays. And honestly, getting started is ridiculously simple. Before we even think about touching the GPU, let's look at how Numba works right on your CPU. We're starting here because it shows just how easy the syntax is. You can literally test everything locally before offloading anything. You basically just apply a simple decorator onto your Python function. We've got the @JIT decorator here, sitting right above a hypotenuse calculation. The very first time that function is called, boom, Numba's compiler is triggered, building a machine code implementation of the function for those specific float inputs. It is really that straightforward to get a speed boost right on your CPU.
Now, hold on, because there is a super vital detail you absolutely need to know about how this compilation works. By default, if Numba gets confused and can't figure out how to compile your code, like say you throw a standard Python dictionary at it, it defaults to something called object mode. You do not want this. Object mode skips the type specialization entirely, which basically means you sacrifice the exact speed you're trying to gain. You might think your code is optimized, but it's actually dragging its feet. So, the golden rule here, you should force no Python mode. By passing no Python equals true to the decorator, or just using the @ngit alias, Numba will loudly throw an error if it can't figure out the types, rather than acting as a silent performance killer. Forcing no Python mode is absolutely the best practice.
All right, the moment we've been waiting for, let's target the GPU. We're looking at NumPy universal functions here, or ufuncs, because these functions naturally perform the exact same operation on every single element in an array. They are tailor-made for a GPU's parallel processing. With Numba, if you're already used to writing standard Python functions, this is the exact moment you turn into a GPU programmer. You simply implement a basic scalar function like our addition function here, and decorate it with @vectorize. You give it an explicit type signature, telling it to expect and return 64-bit integers, set the target to CUDA, and wow, you've instantly turned a basic math function into a GPU-accelerated powerhouse. And here's the really cool part. When you pass your NumPy arrays into that function, it feels exactly like a normal Python call. But automatically behind the scenes, Numba is working overtime. It is compiling the CUDA kernel, allocating GPU memory for both your inputs and outputs, physically copying the data from your CPU host over to the GPU device, executing the kernel, copying the results all the way back, and then returning it as a nice, neat NumPy array. The whole shebang. Also, you don't have to write it in C. It's remarkably concise. But wait, get ready for the classic gotcha moment. Literally every new GPU programmer hits this wall. Let's check out the benchmark for our fancy new GPU edition compared to just a standard CPU NumPy edition. Uh-oh, the numbers kind of speak for themselves here. The GPU took 702 microseconds, and the pure CPU version, just 1.29 microseconds. the GPU is drastically slower. This sparks a pretty great question. Why did our incredible parallel processor just get smoked by a standard CPU? Well, the answer is that we kind of deliberately misuse the GPU in that first example. GPUs excel under very specific conditions, and we violated a bunch of them. First, our inputs were just way too small. It's like renting a massive freight train to deliver a single pizza. GPUs need thousands of values at once just to stay busy. Second, our calculation lacked arithmetic intensity. Simple addition just doesn't involve enough math operations, so the GPU spends most of its time just sitting around waiting for data to arrive. Third, copying data back and forth has a major overhead cost. And finally, our data types were totally bloated. We used 64-bit integers when we definitely didn't need them. Actually, to really hammer home that last point about data types, look at this number, 24x. That is how much slower basic arithmetic on 64-bit floating point data can be compared to 32-bit floats on certain older GPU architectures. 24 times. Now, newer GPUs have narrowed this gap a bit, but remember, NumPy automatically defaults to 64-bit data types. This makes it an incredibly common trap for Python developers. If you forget to explicitly cast your arrays to 32-bit, you might be accidentally introducing a massive, totally unnecessary performance penalty to your code. Okay, let's actually fix those mistakes and see what Numba can really do. We're going to use a Gaussian probability density function this time. Notice the changes we made to build this out. We are feeding it a massive input array, 1,000,000 elements, just to keep the GPU fully busy. We explicitly cast that array to 32-bit floats. We swapped to math.x instead of the NumPy math functions because we're compiling for the CUDA target. But most importantly, this specific equation has high arithmetic intensity. The result? Oh, it's night and day. Even when you include the heavy overhead of copying all that data to and from the GPU, this optimized code will utterly crush the uncompiled CPU version in a benchmark. So we've nailed the computation side of things, but we still have a lingering elephant in the room. Like we talked about earlier, transferring data back and forth between the CPU and the GPU is heavily time-intensive. Our function is still paying that tax on every single call because Numba is playing it incredibly safe, shipping the data out to the GPU and pulling it right back to the CPU after processing. So how do we take the training wheels off? How do we actually stop Numba from making all these automatic return trips? To really grasp why this is so absolutely critical, listen to this direct, authoritative rule from the official CUDA Best Practices Guide. High priority, minimize data transfer between the host and the device, even if it means running some kernels on the device that do not show performance gains. That's right, the absolute top priority in GPU optimization is minimizing data transfer. You want to keep your data physically sitting on that device for as long as humanly possible. We need to be able to run several operations in sequence without ever triggering Numba's automatic return trip to the CPU. And the ultimate fix for this, we manage the GPU memory ourselves using CUDA device arrays. You just import CUDA from Numba and use the CUDA.toDevice function. This literally copies your host arrays directly onto the GPU and returns pointers to those specific device arrays. Now the data is physically living on the GPU. If you try to print it out, you won't even see the numbers. You'll just get information about the array because the actual data isn't on your CPU anymore. You can now pass these device arrays into your CUDA functions exactly like you would normal NumPy arrays. Boom. Training wheels are off. You've completely bypassed that massive copy and overhead we saw earlier. But wait, actually, scratch that. We aren't completely done. We still have to handle the output. Because if we just pass those device arrays in, Numba is still going to auto-allocate a brand new device array for the result and copy that back to your CPU. To stop this, we use a quick two-step process. First, we use CUDA.deviceArray to pre-allocate an empty bucket directly on the GPU. Then, we use a special out keyword argument in our function call to tell Numba, hey, put the result exactly right here in this bucket. Now the entire operation happens strictly on the GPU with zero automatic data transfers. When you're finally done with all your sequential math and you truly need the data back on your CPU, you just call the copy-to-host method. By using that @vectorized decorator, managing your arithmetic intensity, and carefully taking control of your memory with device arrays, you can squeeze truly breathtaking parallel performance out of your hardware. All while using the Python syntax you already know and love. You've officially bridged the divide, and you did it without writing a single line of C++. So I'll leave you with this. With the memory bottleneck fully conquered and the massive power of the GPU literally at your fingertips, what massive, complex data problems will you unleash your Python code on next? Thanks so much for joining me on this explainer, and happy coding.